Hey everyone, on this lesson we are going to use the principal component analysis to make a better visualization of our data. Remember that on the previous lesson we visualized the classes of the data set, right? And now we will improve this visualization applying the PCA technique. Remember that on the previous lesson we discussed that when we have a high dimensionality of the data, this makes it difficult and longer to manage and understand this data. So dimensionality reduction methods such as the PDA, provides us many benefits. So let's add now a new section here. Okay, we can just go to code window, a new code window, and here let's just write PCA. In this case, it's going to be a text window. So here we just add a text window, and here we just write PCA. So here let's add that we are going to use this technique for better visualization. Now, on the PCA technique, we assume a Gaussian distribution of the attributes. This means that the data must be standardized. This will change the data so that all variables have mean 0 and the standard deviation is 1. So here let's add a new code window, and first of all let's standardize this data. So in order to do this, let's define a new data set of the CRABS data. Let's just call it CRABS standardized. So this will be at the end the CRABS standardized data. So initially we will have that this is a copy of the previous data set. So we just copy this CRABS data set. And now we standardize this data set. Now to do this, we will apply the standard scalar. This is a procedure from the scikit-learn library. The scikit-learn library is a free software machine learning library for the Python programming language. This library provides many features, such as for classification, regression, and clustering algorithms, including support vector machines and so on. So it is a very complete and extensive library for machine learning in Python. We will use this library to standardize the data, which is one of the many things we can do with this library. So the first thing we need to do is to import this standard scalar procedure in the import libraries window, right? So we will import this procedure for the scikit-learn library. So we can do it simply in here from the scikit-learn preprocessing module. So here we access the preprocessing. We are going to import the standard scalar. So here we import the standard scalar like so. Again, this is to standardize our data, the standard scalar. Now, since we are already in this window of importing libraries, and since we will apply and use the principal component analysis technique in this lesson, it is also important to know that we will need to import the PCA from this library scikit-learn. So to do this, to be able to use the PCA technique, we need to go to the scikit-learn. Here we will use the decomposition and we import the PCA. Also, we can set the display type of the configuration for the scikit-learn. This is optional. However, in the global scikit-learn configuration, the estimators will be displayed with a diagram in the notebook. If we want the estimators to be displayed as a text, we need to change this configuration. So to do this, it is very easy. We just here from the scikit-learn library, we will import this setconfig so we can change the global configuration of the scikit-learn. This is the setconfig with this underscore. And now we will set the config of this scikit-learn. And now on the display option here, we will set this to be text. Again, this in here, this line, we will ensure that the estimators will be displayed as text and not as diagram here. Okay, the default is diagram. So let's just write here diagram. So if you don't make this change, the display basically is diagram. If you make this change, now the display is text. This is for when you're calculating estimators. Also, when you're working with a scikit-learn, or in fact in any machine learning process or project, it doesn't need to be with the library scikit-learn. we have a thing that is called a deprecation warnings. Deprecation warnings are a common thing in the industry of machine learning, and they are simply warnings that notify us that a specific feature will be removed soon and shall be replaced with something else. So you can visualize this as the idea of warning messages that are typically issued in situations where it is useful to alert the user of some condition in the program where this condition does not raise any exception and does not terminate the program. For example, one might want to issue a warning to the user when a program uses an obsolete module. So there's a way to avoid and to ignore all these warnings that do not raise an exception at all. Here basically ignoring this type of warnings. So here we will import the warnings library in Python. This is a module in Python. So we will import this warnings module in Python. And to ignore all these deprecated warnings, we can just here type warnings, filter warnings, ignore, like so. So this is a general behavior when you're doing machine learning, and this is not mandatory for this work on this project for the PCA. However, there will be occasions where you don't want to have many warnings in our windows, okay, because these warnings do not produce any exception. They are simply warnings that specify the behavior of the data set, how the data set is changing, and so on too. So to avoid all these extensive warnings, we can use this criteria. Very well, with all this, once we have imported the standard scalar, right, we can standardize this data. So we will not yet use this PCA, okay. We will just start standardizing the data. Since as we've explained before, to apply the PCA technique, the data must be standardized. So in this data set, remember that when we did the visualization, right, we only visualize the relevant features. Remember that these relevant features were 5, the frontal lobe, the real width, the carapace midline, the maximum width, and the body depth, right? So now when we visualize these classes of the data set, applying the PCA technique, we will also use only these relevant features, so we will only normalize these relevant features. Also keep in mind that there is no sense, and this does not make any sense, if we normalize or if we standardize the data that is categorical or even binary, right? If we have a sex that can be either male or female, or if we have a species that can be either blue or orange, we have binary values, we have categorical variables, so we cannot standardize this data. On the other hand, it does make the total sense, and it is very important and efficient, that here we have continuous variables, okay, from the frontal lobe until the body depth. These are the 5 relevant features. So since they are continuous variables, okay, it makes the total sense that they can be standardized. So we will basically take all these relevant features, all these relevant attributes, and we will standardize this data. So we will copy these variable data columns. Okay, on these variables we have all the relevant features. So now we will standardize this grabs standardized data, and we will do it only with the relevant features, right? So we will only access here the data columns. These are the relevant features, and here we will use the standard scalar that we have imported right here above on top from the scikit-learn library. We have imported a standard scalar, so now we will use this scalar to standardize the data. So in this sense, now the mean of the data will have basically the mean 0, and the standard deviation of this data will be 1. So to do this, we just applied the standard scalar. We are going to fit this, transforming the dataset grabs data with the relevant features. So here we just write the dataset grabs data, and now the columns that we want to standardize, in this case, all the relevant features. So this is the data columns array, right? Like so. So with this, we will have the data standardized. The data will have mean 0, and the standard deviation is going to be 1. So we can check this with the describe method. So here we just write this new data set standardized with the describe method, and here we can transpose this table. So now when we run, we'll have the description transposed. So before running this, remember that we need to go into the import window and also update this window because we have not run this. We want to import the standard scalar, so we run this again. Now the Google Colab will update this. Keep in mind that here we are only missing an N. Okay, this is further warnings. We add this and we run again. And now we have done all the imports, and now the notebook has import this standard scalar, right? So since now the notebook is up to date, we can proceed for running this cell. And as we can see, here we have the description. Why do we add this T? What does this T property mean? Well, this is basically the transposition of this matrix. Keep in mind that this description is nothing more than a table. It is a matrix that if we erase this T, for instance, let's just copy this in a new code window. Let's clear this output. We can do it in here, clear output, new code window. So if we just remove this T, what is going to happen? Well, we have that now the count, the mean, the standard deviation, all these characteristics is on the left, but we want them to be on top, okay, to have this classification. So we just add a T, and here we transpose this matrix, and now the description attributes is on top, right? So as we can see, we have here the count, the mean, and so on. So why do we do this? Well, we do this, okay, this description to verify that we have correctly standardized all the data. Keep in mind, when we standardize the data, okay, the variables now must have mean 0, the ones that we have standardized, and the standard deviation needs to be 1, also of the columns that we have standardized. Remember that we only standardized the variables frontal lobe, rear width, carapace midline, maximum width, and max and body depth, right? So here we can check, for instance, what is the mean of the frontal lobe? Well, the mean is this value. This is a value that is precisely as minus 7.1, okay, multiplied with 10 raised to minus 17. So this is a very, very small number, okay? This is very, very small, and we can approximate trivially this to 0. So this is 0, practically. And the same thing happens with the rear width. What is the mean of the rear width now? Well, it is 6.04 multiplied in scientific notations with 10 raised to minus 16. This is also very, very small number with many zeros. We have a total of 16 zeros, right? So also there's a 0. As we can see, all the mean, also the body depth, the maximum width here is 0. And what about the standard deviation? This standard deviation needs to be 1. So the same thing happens here. What is the standard deviation of the frontal lobe? 1. What is the standard deviation of the rear width? It is also 1, right? So with this, we verify that all the columns that we have standardized are all correct. We have standardized all data correctly. So apart from only standardizing the data, that's why we advise the student to also check that the standardization is correct, okay? So with this, we see that the standardization is correct. For all the columns that we have standardized, frontal lobe, rear width, carapace midline, maximum width, and body depth, all of them have mean 0 and standard deviation 1. Very well, once we have the data standardized, we can proceed to apply the principal component analysis. So here, let's just write a text window. Remember that you can download all this notebook on the downloadable resources of this lesson. So let's proceed to use the principal component analysis technique. We will do this with the method of PCA that we have imported from the scikit-learn. This method will return the explained variance ratio and all relevant PCA related parameters. Keep in mind that we can use the explained variance in here ratio and the singular values to decide how many components we will keep. Remember that here the components are the eigenvectors of the PCA. So let's apply the principal component analysis technique. We will explain this step by step. So first step, if we use the PCA method, this will return the explained variance ratio and all relevant PCA related parameters. So first let's calculate those. We add a new code window. So let's define a new variable that will have all this information. Let's just call it my PCA, right? And this is going to be equal to the method PCA from the scikit-learn library that we have imported. Okay, here, import PCA. So we will use this module here, PCA, and we are going to fit this principal component analysis to the data set that is already standardized. In this case, this one, grabs standardized. So we are going to fit grabs standardized, right? And we are only going to apply the principal component analysis on those features that are relevant. So in this case, we'll only apply them on the data columns, right? So here we are just going to apply it on the relevant features. Keep in mind that we want to use in the principal component analysis for this problem to improve the visualization, right, that we did on the previous lesson. If you remember the previous lesson, we did an initial visualization of the data set. However, since we had too many dimensions, this visualization was not the best one, right? Because we need to do a lot of work to visualize all the relation between the relevant features and the classes. But the most important thing is that we only visualized those features that are relevant, right? The frontal lobe, the rear width, the carapace midline, the maximum width, the body depth, and this is all. We only visualize these features. So in the same way, when we apply the PCA technique for visualization and this enhancement of this visualization, we will only do it with the relevant features. That's why here we are only going to fit the principal component analysis on the relevant features. So once we have this variable, we can print the explained variance ratio. To do this, we can just write here the print method in Python, here the object of the PCA, in this case my PCA, and we can just access the explained variance ratio, like so. This explained variance ratio returns a vector of the variance explained by each dimension. So since we have here 5 dimensions, we have 5 features, we will have a vector of the explained variance by each of these 5 features, right? So we can print this. We can also print, so to print the cumulative sum, we do the same thing, my PCA explained variance ratio, and here we just access the method of the cum-sum. This is a general method in any array in Python that returns the cumulative sum of a vector. So keep in mind that if this is a vector that each position has the explained variance for that dimension, then this is a vector here, a vector x, that will return, okay, the cumulative variance explained by the first dimensions that we have seen until that moment, in the sense of if we are in the position I, this position I returns the cumulative variance explained by the first I plus 1 dimensions. Keep in mind that the index list in Python starts at 0. That's why in the position I, we have the explained variance of the first I plus 1 dimensions, right? Here, if we are in the position, for instance, the position x2 of this vector, this contains the information of the first 3 dimensions. The dimension 0, the dimension 1, and the dimension 2, because we have the cumulative sum. So with all this, let's print this and explain the result. Right, we can run this. Let's run this cell. So here there is one argument that is missing, and this is because this is a method, so we can just add the parentheses in here. Okay, just in here. We run again, and now as we can see, we have a vector. Okay, we have a vector where each position, okay, explains the variance on each dimension. So here, this value in here is the explained variance for the dimension frontal lobe. This one is the explained variance for the dimension rear width. This one is the explained variance for the dimension carapace midline. This one for the maximum width, and this one for the body depth. Now, we want to reduce the dimensions of this data set. We want to apply a dimensionality reduction. Why is this useful? Why is this explained variance useful? Well, this is useful because since we can know also from this vector, okay, what is the explained variance for the I plus 1 dimensions, we can choose how many components, right? We can decide from these values how many components or how many dimensions we will have at the end. For instance, with the first two dimensions, we have an explained variance of 0.98. Okay, that's a good explained variance. Now, with the first three, we have a value of 0.9974, which is a 99.74%. This is a very good explained variance. So it is going to be a greater idea and a better idea to visualize the data set using 3 dimensions, because as we can see with these 3, we have this explained variance, than with only 2, right? So this is an example where these 2 dimensions and 3 dimensions is close to each other, but it may be cases where this, for instance, the cumulative sum in this position, which is basically the information with the first 2 dimensions, is something like 0.6, and with the 3 first 0.97 or something like this. So in that case, you'll never choose only 2 dimensions, instead you will choose 3. Here it is a good idea to choose both 2 or 3, but it is better to choose, as we can see here, 3, because we have a better explained variance. Very well, now we are going to represent the script plot. A script plot, let's put here with this heading. So this script plot is very, very important when using PCA, and it is important to understand and to know how to interpret this script plot. So why is the script plot used? Well, the script plot is used to determine the number of principal components that we will keep in a principal component analysis in the PCA that we are doing here. So let's do this script plot for this example and see how we can choose the number of components. Again, one way is by the explained variance ratio in the cumulative sum of this vector. So we have until a given dimension how much of the explained variance we can have. But a very common way and usual way to do this in machine learning is by a script plot. So let's do this now, this script plot. The first thing that we need to do is to create a new figure. We will do this with the pyplot, okay, from matplotlib. So a new figure is going to be the pyplot with a better figure. Here we can also choose the size. Let's just say that this is going to be a size of width 8 and height 6, for instance, okay. So we already have the figure. In fact, if we just run this, we know that we have a figure of this size, right? Now the x-axis is going to be the components, right? So here we are going to use the method plot to plot in this figure. The x-axis is going to be from 0 to 5, right? So here we can just say the range method in Python. We are going to start with 1, and then we are going to go until the length of the total dimensions. In this case, we can access the total dimensions with the singular values. So here, if we just write my PCA, there are singular values with an underscore at the end, okay. This is going to be the length of the component. So in this case, 5 components. However, in Python, remember that if you have something like this, range 1, 5, here you'll have the vector or the list, or in this case, let's say you start 1, then 2, then 3, and then 4. So the 5 is not included, but we want to include the number 5 as well, right? So if we want to include the number 5, we need to change this 5 to 6. So since this is 5, which is the total components, we are going to increase in 1. So 5 plus 1 gives us 6. So from 1 to 6, this range is going to be the vector 1, 2, 3, 4, 5. This is only because of the range method in Python. And so then this is the x-axis. Then what is going to be the y-axis? Well, the y-axis is going to be the eigenvalues. Keep in mind that this here will return the eigenvalues of the PCA. These singular values are equal to the 2 normalized of the number of components variables in the lower dimensional space. However, you can just interpret this as the eigenvalues. And then we can also set here an option for the line opacity. This is completely optional. However, we are going to set an opacity of 0.8, which is an 80%. And also the marker is going to be with periods. So we define here the marker to be periods. You can change this to be squares or any other type of marker you want. We are going to use the periods. Very well, with this we have the plot that we want. This is the script plot. Okay, let's comment here, script plot. Now we can also label the x-axis and the y-axis, so it is easier to visualize this. So the y label, this is going to be equal to the eigenvalues, so we can use the method y label from the pie plot. This is going to label this vertical axis, and this is going to be the eigenvalues. So here we just type eigenvalues, like so. And then in the same way, the x label, this is going to be equal to the x label of the components. So this is the components, right? This is merely for labeling the vertical axis and the horizontal axis. Now finally we can set a title to this plot with the title method, and here let's just say that the title is the script plot, like so. So now let's run this code window. We run it, and now we'll see the script plot, like so. Here we have that the horizontal axis is the components, the number of components, and the y-axis the eigenvalues. And if you know, this is just plotting the script and the singular values, right? In fact, if we come here, we add a new code window, and here we just write the singular values, and we run this. This is going to be the array that is basically the eigenvalues for each component. This is the eigenvalue for the component 1, component 2, and so on. So this is precisely what is happening here. The component 1 has a value around 30, which is 30.94. The component 2 a value of 5.5, which is here. The component 3 a value of 3, more or less, like here, and so on. So this is just plotting the singular values. Now the rule of thumb for interpreting the script plot is as follows. What we want to do is to retain the number of components that are above or what is the script, or when this plot tends not to draw much. So we will then say also a flat line, but taper off very gradually. So as we can see, we have a very big slope from the component 1 to component 2, and not so many big slope for component 2 to component 3, and then we have something like a script that really this doesn't change much the slope. So what does this name come from, the script plot? Well, the script is a geological term that indicates the rubble or the stones that fall from a cliff. So if you think of a cliff, you're driving along a road and you're gonna see a lot of stones smaller sized. You're gonna see a lot of stones, smaller sized rocks, then some bigger rocks, but they're all collecting along the side of the mountain, right? Well, this is the scree or the rubble that is collected off the cliff. So that's where this name comes from. So we want to retain the number of components above the scree. So generally, for the visualization, 2 or 3 components are chosen. Keep in mind that the script here we can interpret like with 2 components can be sufficient, right? Because here we have the cliff and here we have the screen. However, for the visualization, we can also here choose 3. So let's continue by plotting the percentage of variance explained by component. So let's add a new text window. Here we are going to plot now the percentage of explained variance by component. So first of all, let's create here a new figure. We add a new code window. We are going to create a new figure with the pie plot figure method. So here we just write figure, the fig size, for instance, let's just say it is going to be 8, 6, and here we are going to return this in the variable figure, right? Now, once we have the figure drawn with the matplotlib library, we can now apply the method plot of the pyplot library. So here we can just use pyplot plot, and here we specify first of all the x-axis, and now the x-axis is going to be the component. So in the same way, we can here define the x-axis as to be the range from 1 to 5, and this 5 we can get with the length of the variance explained with the object myPCA. So remember that this object here of the PCA is myPCA, so here we just copy myPCA. Here we use the method explain variance ratio, like so. So since when we do the length of this, since we have 5 components, this is going to be 5, but in the same way, when you do something like this, you'll have the array 1, 2, 3, 4. But we want also a 5 here, so here we change the 5 to be 6, so we have also 5. So we add the length plus 1, right? So here we just add a plus 1 in here, inside the range method. Now we specify, as any plot method, first we specify the x-axis, right? And now we specify the y-axis. So the y-axis is going to be the values of the explained variance ratio, like so. We can also define the opacity. Let's just say that the opacity is an 80%. The markers is going to be points as well. So here the marker, we just define this to be periods, like this. And then finally, we will add the label here to say that this is going to be the explained variance. So this is the explained variance. And we end this pyplot function. Now we are going to label the y-axis and the x-axis. So the y label is going to be here, the pyplot, and here we just write y label, right? Like so, y label. So this vertical axis is the explained variance. We are plotting the explained variance. And here we are also going to define the x label, the horizontal label. This is going to be the components that we have, right? In the same way here. On the previous plot, we defined and we plotted the eigenvalues for each component. And here we have the explained variance for each component. Very well, so with this plot, okay, we have the percentage of explained variance by component. Finally, we can define here the legend. We can add legends. So now we can have and see the labels that we have written, okay, in a specific for this label, for this function. And now we can here, for instance, set the title of this figure as the percentage of variance explained by component. So let's run this. So here we see the percentage of the variance explained by component. Keep in mind that we add this pyplot legend, so we can see here this explained variance for this function in blue. Now keep in mind that what we have here is precisely the values of this explained variance ratio, right? For instance, for the first component we have a value of 0.95, right? Because here it is 10 to the power of -1 in scientific notation. So this is around 0.195, and this is precisely what we see here. The component 1 has an explained variance of 0.95. What about the second component? Well, the second component has a value around 0.030337. So this is the value that we see here, right? So what if we also want to plot, now in this case we see it here, right? In the percentage of variance explained by component, the component 2 has this value 0.0303. And the component 3 has a value of 0.0093, what we see here, 0.0093, right? So what if we also want to see inside this same figure the percentage of variance explained, but also the cumulative explained variance? So precisely this other array that we saw before. Okay, this is the cumulative sum of the variance explain, such that if we use only one component, we have this variance explain. If we use these two, we have this variance explain. If we use these three, we have this variance explain. So to do this, let's just also plot this accumulative variance explain. This is going to be very important, and we'll do this in the same figure. So here we are going to add a new line of code before the legend and the title. This is going to be another plot. The range for the x-axis is going to be the same, right? The range basically are the components. And now the y-axis, okay, the function, okay, the image of this function now is the accumulative sum of this explained variance ratio. So to compute here the cumulative sum of this array, we need to use a function that is the CumSum function, okay, and this function belongs to the NumPy library. So the NumPy library, we need to import it on top of our code. To import NumPy, we just type here import NumPy as NP. So the NumPy library is a library for the Python programming language, adding support for large multidimensional arrays and matrices, along with a large collection of high-level mathematical functions to operate on these arrays. So we will use this library, the NumPy library, to compute the cumulative sum of this array. So here, okay, on the plot at the end, on the y, okay, here, now instead of just my PCA explain variance ratio, we will compute the cumulative sum of this. And to do this, we just use the NumPy method, that is the CumSum, and as an argument we pass this array, like so. This is going to compute the array that is the cumulative sum of this array. Also, since this is going to be another function inside the same figure, we are going to change the color for this. We are going to put this color to be red. Okay, we can add here this C, this means color in the pyplot plot method. Okay, this is for changing the color, and the R stands for red. So now this function is going to be painted in red. The marker is going to be with periods as well, and finally the label. Okay, now instead of the explained variance, this is going to be the cumulative explained variance, right? Like so. So here we change this V, we change also this V. And so we end this pyplot method, right? We end this plot. And with this we are done, okay? We are ready to plot now this second function. So now let's run again this cell. We press the run button. And also here, before pressing this run button, let's load again the library window. So with this, we are going to import this NumPy. We need to update. Very well. Now that we know that the notebook is up to date, we can run again this cell. And as we can see here, we see the plot of the explained variance, but also cumulative. So this red function is the cumulative explained variance. We can see it here with this label. Remember that this title, okay, this legend corresponds to this label, and the blue function is the explained variance for each component, which is here this label, right? So with this, we can see how many components does it take to get a very strong value for the explained variance. Keep in mind that a value that is the very closest to 1 is the best value that we can have, okay? But normally for visualization, we will choose around 2 or 3 components. We can also visualize the weights that the PCA assigns to each component. So here, let's add a new text window. Let's comment this, and let's see how we can visualize the weights that the PCA assigns to each component calculated. So we will use now a heat map. We can use a heat map with the scikit-learn library. And also with Seaborn, we are going to use this library Seaborn with the S and Ls to apply this heat map. So we go here to the window at the end of the notebook, and now we are going to use this library of Seaborn, and we are going to use it with the heat map. The heat map plots rectangular data as a color encoded matrix, such that we can see the weight values and also the color of these weights. So the first argument is the data we want to see the weights of. So in this case, it is the components of the PCA. So we access the my PCA object, and here we just say components. Then the second argument is the C map, the color map. This is just the mapping from data values to color space. There's a wide range of color maps. We are going to use for this example a seismic color map, but you can use any other. So here the color map, the C map, is going to be seismic. Now this third argument is very important, and this is the labels for the ticks on the x-axis. So since we are plotting the color map for the components, now the x-axis is going to be the relevant features, right? So here it is important that you remember, let's add here the code window, that for instance, if we visualize the Colab's data with the head function, right, and we run this cell, we can see the first 5 elements of this data set, right? Keep in mind that what are the relevant features? Remember, the relevant features are the frontal lobe, the rear width, the carapace midline, the maximum width, and the body depth. So we have here 5 features, right, that start at which position? Well, we can see that this position starts at the position 3. So the idea, we are going to start from here, the position 3. So this is basically position 0, position 2, right? Position 1, then we have position 2, and finally the position 3. So we are going to start with the position 3. Until when? Well, until the body depth. So the body depth is the previous element to the last element, because we don't want to have here the class, okay? Only the body depth. So here we are going to use the -1 in Python to just jump to the previous element to the last one. So let's explain this step by step. Essentially, this is going to be the list of the Colab's data, which is our data set, right? And here we are going to select the columns that start at, as we've said, at position 3. This position 3 is the frontal lobe, right? 0, 1, 2, 3, and it's going to end until the body depth. So to select this last but one value, basically the previous one to the last one, we can here use the notation until -1. In Python, when you use here -1, you are getting all the values until the element that is previous to the last one. So we are not including the class argument, because if we change this to be like this, then we will be including the class column. Since we don't want to include the class column only until the body depth, we want to include until the element previous to the last one. So here we use the -1 notation. So with these labels for the x-axis is going to be those columns: frontal lobe, rear width, carapace midline, maximum width, and body depth, which is precisely the relevant features. Now the next argument on this heatmap method is what is called the v minimum and the v maximum. These are the values to ensure the color map. If we don't give them, otherwise they will be inferred from the data that we have. So we are going to select them and to indicate them to this function. Again, these values is to ensure the color map. So we will start with the vmin. This argument is going to be the minimum value, or in other words, since those weights can be negative, it is going to be minus the maximum of the absolute value in the principal components. So this is just the my PCA components, like this. And then what is going to be the value for the maximum in the range? Well, this value for the maximum is going to be the same, but without the minus, right? Without the minus sign, like this. So essentially what we are saying is that these values, vmin and vmax, are values to ensure the color map, right? So this color map is going to be in the range from the minimum, which is the in negative of the maximum value of the weights on the components, and the maximum is going to be basically the maximum value on the weight of the components. So now the color map is ranged from the values that we have on the data set. Now there's an extra argument in here, which is the annotation. And this argument is a Boolean argument. It can be true or false. If we set this argument to be true, then the data is going to be written, the data value, in each cell of the color map. Okay, we are going to visualize the weights inside each cell, and we are going to set this to be true so we can visualize easily those weights. If you set it to be false, there's no problem. However, you will only see the color and not the specific value for each cell. We are going to set it to be true. So with this, we have the heat map of these components. So let's run this cell. And as we can see, okay, with this function, we can see the weights that the principal component analysis assigns to each component. For instance, consider the component 0. This component, okay, the PCA assigns a weight of minus 0.45 for the frontal lobe, minus 0.043 for the rear width, and so on. So as we can see here, as greater is the weight, okay, as more red is the weight, more important it is this component with this feature. So imagine with this component 1. Well, the component 1 is very, very important because the weight is very big for the rear width. So we can explain a lot of variants of this attribute with this component. Okay, for the component 2, we can see that the maximum width is explained a lot because the weight is 0.65. Keep in mind that all of those weights range between 0 and 1. Okay, mainly if we don't specify the values. If we specify it, we have our own range that we can see here. It is from minus 0.8 until the 1 value. So precisely what we have here is minus 1 and 1. Okay, so here the range of the possible weights is from minus 1 to 1. The closest is to 1, the more important is this attribute for this component, right? Very well, so with all this information, now we can proceed to visualize our data so that we will now transform our data set using the principal component analysis technique. In fact, it's going to be a trained principal component analysis. And generally for the visualization, and this is commonly using 2 or 3 components. Okay, so normally 2 or 3 components are chosen for the visualization. So here we are going to add a new text window. We are going to set this to be a title, and this is going to be PCA transformation and visualization. So this is applying the PCA technique. So let's just also paste here that we can transform now our data set using the trained PCA, and we are going to choose 2 or 3 components. Okay, so let's use for this example 3 components, and let's define this new data set to be transformed. So this is going to be the transform data set of the grabs data set. So to apply the PCA, we need to access the PCA object and use here the function transform of the PCA object. Here we will pass as an argument the dataset. So keep in mind that this dataset is the standardized dataset, so it is grabs standardized, and we are going to transform only the relevant features, the ones that are continuous variables, right? So we can access here the data columns as the relevant features. So once we have done this transformation, now we have this dataset transformed. So now we can define that on the dataset scraps, or in this case grab standardized, we will define 3 new columns for the 3 new principal components, one for the principal component 1, another for the principal component 2, and finally the other for the principal component 3. So we are going to insert here 3 new columns. So we add one for the principal component 1, another for the principal component 2, and finally the one for the principal component 3. So these 3 new columns are going to have the value of the first 3 components of the transform data. So here we will only define and use the first 3 columns. We will use all the instances, all the rows, and here we will only use the first 3 columns. And to represent this in Python, we write here 2 points and then the number 3. This means that we will cover the column 0, column 1, and column 2, which is basically these 3 principal components. This stands for all the rows. Very well. So once we have this, let's create a new figure, and we are going to use now a scatter plot So here, figure is going to be the pie plot, figure method with this size, 8, and now we are going to use the seaborn scatter plot. So here we just use scatter plot. And let's first visualize the first two components. So here we are going to visualize the first two components of the PCA, so that the x-axis is going to be the principal component 1, the y-axis the principal component 2, right? What is going to be the hue? Well, remember that we need to do this visualization as we did before with the classes. So we need to really visualize the classes of this data set as we did on the previous lesson, right? We did the initial visualization. So we do the same thing, but here applying the PCA technique. So now the hue is also going to be the class. So here the hue of the scatter plot is going to be the class feature. And finally we pass the data, so the data is the crabs standardized. So here we can plot now the scatter plot. Remember that a scatter plot is used to plot data points on a horizontal and vertical axis in the attempt to show how much one variable is affected by another. So before running this cell, keep in mind that this function normally returns a value, but if we don't want to return this to any variable, we can just use here an anonymous variable. This means an anonymous variable in Python, a variable that we will not use at all. We only want the visualization. So let's run this. And before running, let's run this transform data so we can transform like so. Very well. In fact, if here we add a new code window and now we visualize the standardized data set of the grabs with the first 5 rows, for instance, we will see now these 3 new principal components, which is basically these 3 new attributes, right? This is because we've done this instruction in here. Okay, we've added 3 new columns that have these values, which is the values of the transform for the first 3 principal components. Keep in mind that this transform array has the information of the 5 components, and here we are selecting only the first 3, right? So here we have PC1, PC2, and PC3. Very well. Once we have this data and also updated to the grab standardized head, we can visualize the first 2 components on a scatter plot. So now let's run. And as we can see, here we have the scatter plot on the principal component 1, the principal component 2, and also this visualization for the classes. The blue points are for the blue male grabs, the orange for the blue female, the green for the orange male, and the red for the orange female. Keep in mind that principal components are created in order of the amount of variation they cover. The PC1 captures the most variation, PC2 the second most, and so on. Now, when we do a PCA plot, this plot shows clusters of samples based on their similarity. Because as we can see, the objective of this project on the grabs dataset is to separate these 200 of grabs into 4 classes, right, depending on the male, female, and blue-orange. That's why we apply the PCA, the principal component analysis. So since when we apply the principal component analysis, we can see that the group, the class blue male is this one, okay, the other group blue female is this one, the other class orange male is this one in green, all in the same region, and finally the orange male, orange female is this on red, all in the same region. So as we can see, this separation is precise. We have here 4 groups depending on their similarity. So with this, we can separate these 4 classes as the project statement specifies. So we can see that the principal component analysis does a good job with this data separating these clusters. We are using for this visualization only 2 principal components, right? So now to end this principal component analysis visualization, let's do the same with 3 components, right? So now we are going to visualize this. Let's put it in here with 3 components of the PCA. And to do this, we're also going to do a scatter plot, but now with 3 dimensions, right? We'll have a 3-dimensional plot. So the first thing we are going to define is the mapping between the colors and the classes of these grabs. So imagine if we have the class blue female, right? So this class blue female, we will set this to be yellow. Then the next class, blue male, we will set this to be with the color blue. So we write the B. So we are basically mapping each class to a given color. Then the orange female, we are going to set it to be orange. So we just add here an O. And finally, on this final class, orange male, we are going to use the color green. So we just add here a G. So this is nothing more than a dictionary. It is a mapping that given a class, we know its color, okay? Where the classes are the keys and the colors are the values of this dictionary. Very well, so now let's create a new figure, as always, with the pyplot figure. Now, by definition, when we use this method, this creates a two-dimensional feature, in this case figure. If we want to add a third dimension to have a three-dimensional plot, then the axis is going to be the figure, and we are going to add a new axis. So here we just can use here the add subplot method, subplot. So we want this additional axis to be a grid of 1 times 1. So here 1 times 1, and we want it to return also the first and only axis object in this grid. So that's why here we set 1, 1, 1. Finally, we specify the projection, and this is where this comes from, the 3 dimension. So here we just add 3D for the 3-dimensional plot. Very well, with this we have the figure in 3 dimensions prepared. Now the only thing remains to do is to do this scatter plot. To do this, we will use the method scatter from the pyplot library. Now we specify the 3 axes. The x-axis is going to be the component 1, so we access the grab standardized and we access this column, the principal component 1. The y-axis is going to be the principal component 2. Here it is standardized. The same here, and finally the z-axis is going to be equal to this third component. And also there's more arguments in here. We can also set the depth shade of this scatter plot to be false, in the sense of this depth shade basically is the point opacity relative to the depth in the matplotlib 3-dimensional plot. So if we don't want the points of this plot to have more opacity or to have less opacity depending on their depth to the plot, we set this to be false, and this is precisely what we'll do. We're going to visualize all the data in this 3-dimension without any opacity changes. So we define the depth shade to be false. So there's no shading in respect to the depth. So finally here we define the colors, right? Now remember that here we define that just the scatter plot and the colors were automatic. Here we define a dictionary that for each class we have a color. The blue female yellow, blue male blue, orange female orange, and orange male G. So to apply this dictionary inside this color, one possible value of the color is to apply essentially this dictionary. So we are going to access the data set and the column class, and we will apply this mapping process that if we have a given value x, okay, we will return the value of this color grabs of the x. So here color grabs for the value x. So keep in mind that what we're doing here precisely is for a given class, a given blue female, blue male, orange female, or orange male, we will return and we will apply the color y, b, o, or g depending on this value x. So we return here the value of this dictionary. This is a lambda function. We will not go inside how this is implemented, but this is mainly a function that given one single argument, we return this as an output. And this is precisely the color that we will apply for all this scatter plot. Depending on the class we have, we'll have different colors. So this is colors with an S. We in the final parentheses of the scatter plot. And also here before running, we need to import the possibility of using 3-dimensional plots in matplotlib. So to do this, we just go to the import window, and here we can simply import this configuration, and this is nothing more than a toolkit. And in here we can do this, for instance, like here, and we just write from the matplotlib toolkits, we import from the module 3-dimensional matplotlib, we import here the module axis 3D. So we run again this code window, we update the notebook, and now we're ready for running this cell. So we run it, and before running, we're also going to specify the marker size. For instance, let's use a marker size of 800. This specifies the size of the marker. We run it, and now, as we can see here on the plot, we have the PCA visualization for 3 principal components. We have that the x-axis is the principal component 1, the y-axis the principal component 2, and the final z-axis the principal component 3. We also have that if we have a crop that is blue female, the color is yellow, so this yellow is the cluster, the group for the blue female. If we have a blue male, this is the color blue, we have this group. Orange female, the color red, we have this other group. And finally, the orange male, we have the color green, which is this other group. So with this principal component analysis visualization with 3 components, we can also see here all the cluster samples based on their similarity, because our objective in this project is to separate all the 4 classes, right? And with this, with the PCA, we have done this. First, we did it with 2 dimensions, with 2 principal components. We have these 4 clusters, and this visualization, this separation is even more pronounced with 3 principal components in this 3-dimensional plot. Okay, with this, we separate all the 4 classes, all these 4 clusters with these 4 groups. We can also visualize those components finally in 3 dimensions using the Plotly Python library. This is an interactive open source plotting library that supports many chart types covering a wide range of statistical, financial, geographic, scientific, and 3-dimensional use cases. So to import the Plotly, we just go to the import window, we import here the Plotly Express as the PX. Okay, we'll use this Plotly Express library to do this scatter plot in here at the end. So we will add now a new code window, and now with the Plotly Express library, it is very easy to create this scatter plot in 3 dimensions, and also much shorter way than before. So we are going to define the figure using the Plotly Express library as the PX. This is the Plotly scatter 3-dimension. This is a method from this library. Here we specify the data. This is the graphs standardized. Then we'll specify the x-axis. This is the principal component 1. The y-axis is the principal component 2. And finally, the z-axis is the principal component 3, right? What is going to be the color? Well, the color is going to be depending on the class. Okay, if we have one of these classes, depending on the class, we'll have a different color. Very well, and with only this line, only one single line, we can see and construct this scatter plot. So finally, we can just show this with the figure show. With this, we are showing this figure that we have just created. So let's run this. And as we can see, we have here the scatter plot in 3 dimensions of the 4 classes. So we have separated these 4 classes with the principal component 1, 2, and 3. In fact, we can zoom this in, zoom this out, and we can see here the 4 groups, right? If we have blue male, these colors is for the colors in blue. The red is for the colors in blue female. The green is for the orange male class, right? We have also this other cluster, this other group, and the purple for the orange female. So we have here this final group. So with this, we have applied the PCA technique and also done the visualization of the classes with, on one hand, 2 principal components and also with 3 components on this PCA. We have done it with the scatter plot for the matplotlib library and also the 3-dimensional scatter plot of the PyPlot Express library. We have separated all 4 classes of this dataset with 2 principal components and also with 3 principal components. We remind the student that you can download all this code and this notebook on the downloadable documents of this lesson. Okay, here you have available all this notebook from the initial point, where we studied all the graphs data set, right? We did our initial visualization of the data and also with the classes, right? And then we applied the principal components technique to reduce these dimensions, and we visualized these 4 classes, and we separated these 4 classes with 2 components and 3 components. All of this code and all of this notebook is available for downloading. With this, we end this practice on the dimensionality reduction, applying the principal component analysis technique.